Hello everyone, my name is Mads Barami from Wolfram Research. Welcome to the third session of our live coding series with Andreas Lauschke. As you may know, Andreas will do live demonstration of key features of Wolfram language that are useful in data science. I already mentioned that, but let me rephrase that. Andreas has a master's degree in financial mathematics from Technical University of Berlin, and he has been using Wolfram technology for about 25 years. Today, Andreas will talk about association and dataset, which will be the second session on this topic. If you missed the previous sessions, you can watch them on our Wolfram channel on YouTube. Without further ado, let us welcome our instructor, Andreas Lauschke.
Great, thank you. Hello, everybody. So yes, today is the third live coding session, and that is the second part on associations and dataset. So I'll be talking about that one today, and I'll be primarily using hierarchical data. In the last session, I was using tabular data, but associations are so powerful. They represent, as you know by now, key value pairs, and that makes them incredibly powerful to model trees, for example. And in the next session, I will finish up on associations and dataset and introduce the query. The query is incredibly powerful, and it's used under the hood by dataset, but it can be used outside of the dataset. There's no need to tie it to that. The query is incredibly powerful also for the manipulation and analysis of raw data. And then in the session after, I will show some techniques and methods for what I call web scraping. The greatest dream of the data scientist is free data, right? What can a data scientist want more than free data? So I'll show some things of like traditional data scraping, HTML parsing, XML. And since version 12, we now also have the wonderful function web execute, which even allows you to run JavaScript directly from your Mathematica system. So it's incredibly powerful, and I think you'll be quite impressed that you can run actually JavaScript code from your Mathematica session. So before I begin with today's session, in the last session, I promised that I would look into the audience questions that we had, and I will begin with that, as I will always try to answer the questions at the beginning of the following question. So there were two questions. One was about JSON stat and PC access. And the authority on JSON stat is their own website. You see that here, json-stat.com. And what it basically is, JSON stat is a particular JSON flavor, right? No more, no less. It is one that is geared toward a particular format that's used in statistics. And they have their website. And in the Mathematica system, it's trivial to handle JSON, right? All you need to do in an import is provide a file that ends with JSON, and then import is smart enough to properly import it, recognize the format, and so on. The export could be a bit trickier because now you have to follow the rules, but reading it is totally easy because JSON stat is just a particular subtype of JSON. So what I have done is that I've gone to their website and just looked at some of the examples. They have a test section, and I've just looked at some of these examples that they have here. Let's import the data. And I haven't gone through everything, but once I noticed that I can handle the simple cases here, the simple examples, I was satisfied. So we read it in, we import it, and you see here the data in a JSON format. And when I was able to extract some of these examples they show here, I was satisfied and just decided to go on and thought it works. So for example, number of observations, I'm extracting the length of the value field here, and it matches 432, right? There comes an update date, 2/12/11/27. Let me keep this on top here. Yeah, where should I put it? It's not a convenient format on the browser. All right, so then I just scroll it. Get the source. and I get Economic Outlook number 92, December 2012, OECD annual projections, right? The next one is a note. Most of the data in this data set are taken from, and so forth and so forth. Seems to be working. Contact information. So this is 2 levels, so I had to use parentheses and go right to left, and then we get eco-outlook OECD.org. Get the address of first metadata file. We have that here. It's the same PDF. Get the number of dimensions and so forth. So it works, right? We can understand it relatively easy, and it is a very promising data format for statistics. And it's just a subtype of JSON, so we have no problems handling it in the Mathematica system. PC Access, it's a statistics program used and developed by Statistics Sweden and Statistics Denmark. And the format is essentially a CSV or a TSV file, a tab-separated values file with headers. And at that point, I also lost interest, right? Because this is relatively trivial for us to handle, to manage. I think CSV is one of my favorite, if not the most, my favorite data format for rectangular data. So here's the link. Here's the website. So they have a corresponding program that comes with it. And if we're talking about the format, then it's trivial for us to handle in the Mathematica system because it's just CSV and TSVs with headers. All right, the other question was about dynamic together with the data set. And yes, it's trivial, right? It works. So let me create a 5x5 Hilbert matrix. I'll display it as a data set, and there you see it. And now all I need to do is change this one, and note that I'm only changing the first line, right? I'm not messing with the data set, but the moment I'm changing it here, I get the new updated version, right? 5, 8, 12, and so forth, right? It's not a problem to use the data set together with dynamic. All right, good. So let me continue with the program. The associations and data set, my second part. Today I focus on hierarchical data. So trees are wonderful in life. They're the best way to model hierarchical data. And associations are a great way to represent trees, as key value mappings are very efficient building blocks for hierarchical data. Technically, even every map, even a simple one-element map, implies a one-branch tree. So let's create an association where we assign several people to other people. Think of this as a corporate hierarchy or whatever other type of hierarchy we have, and we do a tree plot of the normal. So what we can see here is that we map people to other people, right? Mike to Sue and Stan to Sue, and the tree then just shows us this view. And it's relatively easy to see, right? And it worked out of the box. And again, I can't overemphasize it, how code-efficient this is, right? Try to do this in other languages. Try to do this in other languages. What I had to do here was really focus on the structure of these associations itself, and then do a tree plot. And that was it, right? I was able to tell the system what I wanted to do. I didn't have to tell it how to do, right? Extremely efficient. Let's do a quick check. We know from graph theory that the number of edges in a forest is the number of nodes of the forest minus the number of connected components. That's a tree. The tree is the connected component. So it's n minus k. Pick k equals 1, and you get a tree. A forest with one tree is called a tree, or alternatively, a tree is called a one-tree forest. So here we have two trees at the same time connect components. It's a two-tree forest. Here's the larger one, and here's the smaller one. So the length of the association is 18, and we can turn this into a graph, look for the edge list and the vertex list, and it's 18, right? We have 20 nodes. If you want to count the names, it's 20. If you want to count the arrows, it's 18, and we have two connected components, therefore 20 minus 2 is 18. Checks out. All right, so now let's assume that Carol will no longer work for Sue. Carol is, where's Carol? Here, Carol and Sue. But for Kathy, right? So Carol will now be under Kathy. And the Jenny's group, the entire group, which is now separate, gets integrated and will report to Peggy. And the beauty here is all we need to do is repointer these names. It's two changes that we need to do. Jenny will now report to Peggy and Carol will now report to Kathy. That's it, right? All we need to do is repointer two of these elements and look at the new tree plot, and there we have it, right? Jenny now reports to Peggy. Here's Jenny, here's Peggy, and Carol to Kathy. Carol to Kathy here, which means Sue now only has 2 people reporting to her, and Kathy has 4 people reporting to her. All right, and we see that later assignments override earlier assignments. You will also see that we remove Carol to Sue. We just repointed Carol to Kathy, right? You see this here, up here, and we can immediately overwrite this. Very simple to do. This actually means that the keys form a set, and I'm going to talk about this later. A set is a union where every element occurs only once. All right, so to emphasize this, I've got a pretty dummy example here. 1 goes to 2, but then 1 goes to 3, then goes to 4, and then goes to 55. So what will prevail? Well, the 1 goes to 55. That will prevail, and the tree plot shows the same. All right, so that means we have a very easy prune and graft just by repointering association elements. Pruning means cutting the tree, and grafting means implanting something into a tree. All right, and let's do the edge check and the vertices check again. We now have 1 connected component, right? This is 1 big tree now. And we still have 20 names. We didn't remove any person, so it's still 20 people. And if you want to count the edges, it's now 19, and that's 20 minus 1 is 19. All right, so now let's change a few things further. The way to remove in an association is you can use unset, and you can also equivalently assign the dot with an equal sign, right? That is the short form of unset. And typically, sometimes when you want to do those things programmatically, it's easier to use the built-in keyword unset. Sometimes it's easier to handle it with an equation. So these 2 here are equivalent forms. You can also use delete, and we want to remove Chris here, and then we ask for the key, right? The key of Chris. That's where we want to go in the association and delete it, and we have to reassign it to association. I'll talk about that later. We have to assign because delete itself doesn't reassign. So let's do that. So now we've cut these legs, and suddenly we have 4 subgroups, right? We have cut 3 edges. This here cuts 3 edges. So before we had 1, and now we have cut 3 edges, which means we get 3 additional trees. So we now have 4 trees. And let's do the check again. We still have 20 people, minus 4 trees gives us 16 edges. All right, all is good. On a related note, you may prefer dealing with graphs directly instead of tree plot, right? Tree plot is only for trees. Well, it says it in the name right there. And trees are special cases of graphs, so not the other way around, right? Every tree is a graph. Obviously, not every graph is a tree. So you can also use graph and plot it this way. You may prefer this layout because now you can clearly see that Jenny reports to Peggy. Up here, it's a little bit more difficult to see, right? Because Jenny has 3 incoming arrows and 1 outgoing arrow. I'm not going into formatting. There is like a billion options for formatting the tree plot and a billion options for graph. There in the help browser, I could perhaps make a session or 2 about graphs at a later time. This is with default formatting, and I'm not going to go into these layout options. There is tons of possibilities. I would be talking for like half a year if I wanted to go into all these options. So, and we also can get the edges and vertices from the graphs. All right, so now let's do a little bit more on associations. Remember, they are ordered pointers with unique keys. The way it's handled is that duplicates are removed. So when I have 3 goes to 4, and then again 3 goes to 4, well, duplicates are removed. You can see it as repointering the first one with the second one, but at the same time, the keys have to form a set. So that means the second one prevails. And we don't need 2 times the same thing, so we only get it once. All right. Looking up by value will obviously not work in a tree, right? It cannot. What would you do with multiple keys having the same value? So if you're trying to look up 2 in an association element, 1 goes to 2, then we get the smart error message that tells us exactly what the problem is. There is no key 2. There's a value 2, but lookup is obviously by key, so this is not going to work. But notice that this isn't just doesn't work, but that you also get the head missing, right? Which will allow you to handle such cases subsequently. You can now use this in the code programmatically. Subsequently in your code, you can handle missing, and you can also handle why it was missing, right? There can be many reasons for data to be missing. It's a very smart way to tell you, right? It tells you that the key 2 is absent, but it allows you to continue in your code, and you can handle it in a smart way, other than just giving you very undesirable side effects. So if you ever get confused, right, again, use full form, and the head of this error message is missing, but you can get the full information with the full form. Head only gives you the head, which is missing. All right, same as looking up a key that doesn't exist. Well, trying to look up a value is the same, unless it happens to also be a key, but then that's a different objective. So try to look up key C, and A goes to B, obviously that doesn't exist. And these 2 here, well, if you're trying to look up 2 in this, it's not going to work. We just had this. But 2 exists as a key in this example. And what do we get? The value, which is 4. All right. You have to be careful that you pick the right type for the head in the key specification. Here we have one where one key is just A, the symbol A. It's a symbol. Look, it's blue. And the string A. So these 2 associations are the same, but the lookups are different. So obviously we get these 2 different results now. One is C, one is B. So be careful not to accidentally make strings or put them back into symbols or expressions. If the association has a name, which we call symbol, you can look up from that symbol. So let's look at some of these here. We have 1 goes to 2. Here we have an association that itself is a key. A goes to B, goes to Kathy. Red goes to green, and Elvis goes to Presley. So if we look up 1, we look up by the key here. We can also compute this first, gives us the same results, 2 and 2. And here we look up by a key, which itself is an association. It works because an association, all expressions are valid for keys and for values. So we get Kathy. And if we look up red, we get green. Here we are. But keep in mind that associations are ordered. So you can also look up by position, right? If we just look them up by 1, 2, 3, 4, we get the 4 values of these 4 association elements. You can also look up with the built-in symbol lookup. We want to look up 1, and that gives us 2. We can look up by the key, that's the association, by red, by Elvis. All right. Lookup has a third argument for error handling. If it doesn't work, well, then we can just let it proceed in the code, but that's not desirable because we want to be able to have some smart error handling. So we don't have a key Poland in blah, so we return $fails. Another way we can handle is that we can prescribe an action, and print is a side effect, print error. Or we can instead compute output another computation, right? We can give a computation. So this would really effectively allow you to take branches in the code. If it's in the list, fine, continue that code branch. If it doesn't, then call another function here, right? You could call another function here. This could, for example, be a database connection, right? Or a log file. If it worked, great, connect to the database. If it didn't work, all right, write into a log file or whatever. right? You can look up multiple keys at once. So this is what you would put into a list. So here I want to look up 1, we got the result. I want to look up Elvis, we got Presley. I want to look up something else that didn't exist, and I'm getting this message here. I can output $failed when we don't have it. Here, that's a preferred method. Or we can look up, or we can compute something else there. You can also look up a key in multiple associations. Note this is a list of associations in the following here, right? So this here and this here. So blah we had already defined. Here's a new association. Here's a new association. And here comes a list of the things that we want to look up, right? So we have 3 associations here. So 1 in the first one we can look up, that gives us 2. Red in the first one we can look up, it gives us green. Now we're coming to the second association. That's where we get a second list here. 1 has a value 5, we get it. Red doesn't have anything defined here, so we get $failed because that's what we specified here as our error handling output. And in the third one, 1 goes to Germany, we get that, and red doesn't have anything in there. So from the help browser, right, we can have a key that's looking up something in multiple associations, or we can have several keys that look up something in one association and the default. All right, but we also can use the part notation. And with strings, we can look them up directly. And you can therefore use single bracket and double bracket. This results in the same thing, right? The part of river or a simple function application. This is function application when you use the simple bracket. We want the first part, not 1. That's why we're using part here. This is an important difference. So if we look up 1 here in the part context, this means the first element. Well, the first element is January goes to February. We get the value February. If we look up 1 in the association itself, now we're not using part. Now we're just looking up the value 1. I'm sorry, the key 1. Then we're getting a 66, right? So note that part behaves different, but that is so cool because it is ordered. The association is ordered. But that means that we can also take it from the end, right? So I say -1, so now I'm going from the end. And notice we're getting the 66. That's not because it's a 1, but it's still because it's the last element. Or we can use whatever other form we want to use in part, right? This means go from the first one to the last one in steps of 2. And you're getting it, right? Here's the first one, the second one, the third one, and the last one, right? So we get 4 elements back in this new association. All right, as the keys in the association are unique, you end up with the keys forming a set. The definition of a set is that no element can occur twice. And we can use that to build up an association incrementally, but you have to assign an expression that represents that association, and that's a big gotcha. So let's start with the empty one. We insert a new element, A goes to 1. What do we get? We get this 1 element set. And when I say set, this really refers to the keys of the association. Insert a second element. So I say set B to 2. All right, so now we have 2 elements in that association. Override the value of an existing key. So A already has a value, but we're saying A goes to 7, and that effectively has overwritten that element. Now, 2 things. We did not insert a new key value pair of A with a value of 7. That wouldn't work because the keys have to be unique, right? So it didn't insert a second one with A goes to 7. That wouldn't work in an association. Then we would have a second key A, but that's illegal for a set. Instead, we changed the value for the key A, right? A is now 7, used to be 1. Another way to change the value of an existing key or to insert new key value pairs is with associate 2. So we are now creating a new element. A goes, okay, a changed element. It's not a new key. A goes to 88 is now put into this. So again, we've changed the value. But C doesn't exist yet. So when we associate 2, then we get an additional element here. All right. To insert new key value pairs, we can also use append to. So let's append D goes to 123. And append to, append means insert at the end, right? Just like in a list. So it put D goes to 123 at the end of it. But there's also prepend to. Remember, an association is ordered. So if I'm now prepending, then I'm getting the new element at the beginning of the association. We can also use insert to specify the exact position of the insertion. And in the following example, C is in the 4th position. So this will insert M goes to 66 in the 4th position. So we are doing that here. C is in the 4th position. So that's where we're going to insert M goes to 66. And you see that this is in the 4th position. However, insert is not a to function. So it doesn't store it in set. So we specifically have to assign it. You see that when we're looking at set itself, then M goes to 66 is missing. This didn't store it, right? So to keep it, we have to assign it back to set. So if we do it like this, set equals the insert, here was no set equals, then we are getting set with that persistent value here, M goes to 66. Or we specify the position directly in the 3rd position, right? Insert P goes to 77 in the 3rd position. This is the 3rd position. And again, it didn't keep it, right? I didn't say set equals. And now if I do, then we do get it in set. All right, so insert Q goes to 88 in the second last position and keep it. There we are, right? Q goes to 88 is now in the second last position. Removing elements. Use unset. That works great. So we're now throwing out the element that has A as a key. So you see A goes to something is gone. Or use delete. Remove the 3rd element. That's B goes to 2. And we'll store it. Right? So B goes to 2 is gone. All right. So if we don't know the position, then key is the key, because key looks it up by key and we don't have to worry about position. In many cases, we will never know it. So the key of Q, right? And here I didn't specify that it was the second last position. Well, that's why I use key. And then I delete it, reassign it to set. Now you see it with Q goes to something removed. You can do multiple deletions at once. Remove M by key and 1 by position. So here we remove M by key and 1 by position. And note that this is a 2-element list, and every position that I want to delete here itself is a list. It's a 1-element list. And this is important. I'll show you in a moment why that is. So here I'm removing M, the key M that was here. M goes to 66. And then I remove the 1st element, and that was 1st goes to this number. All right, if it doesn't work, you get sensible error messages. If you try to delete by position, you get an error message. If you try to delete by non-existing keys, nothing will happen. So let's try it here. A key R doesn't exist, and an 18th position doesn't exist. So we get an error message, and we get what we try to do. This is different behavior from trying to look up keys that both don't exist. R doesn't exist, N doesn't exist. What happens? Nothing, right? We get the association returned, and even if you do it with 1, we get the association back, no changed. Set remained unchanged. We look at it, yeah, unchanged. So I don't want to talk about some subtleties that you can have here. If you remove key P, then C goes to 345 is now in position 1. And I think I should show you first what this is going to do. So if we have this, if we remove P, then this one would be in position 1. And then D goes to 123 would be in position 2. Imagine the first part done, the second part not yet done. So by removing the second element in the second step, you actually remove d goes to 123, because after removal of p, d goes to 123 is in the second position, although it was in position 3 of the input provided, right? This may seem a bit confusing, but it is the way it is logically. After I remove p, c goes to 345 is in the second position. Then I remove the second element, which was this one, which leaves me the set is now only this one. C goes to a 345. Careful with the nesting level. Let's first add an element that has a list as a values and then remove a particular element of that list. So I'm now inserting a range of 8 under the key L, right? You see that, we see that here. This is now an association of 2 elements, one with the key C and one with the key L. And now what I'm doing this, that I am deleting from the key L the third element. And note that now this is a list of 2 elements. Unlike the syntax we had here, this was a list of 2 one-element sublists, right? So this without the sublists now implies nesting. So we look up the key L, that is here, and here we're now removing the third element, that is this 3, and you see that there's nothing between 2 and 4. All right, note the difference between delete, where you have a list of sublists versus a list of atomics. All right, if we now keep removing the third element, you see that, well, the third element here was 4. If we remove the third element, then we get 5 following 2. All right, let's insert another one under the key H, the 8x8 Hilbert matrix. We can go further in these nesting levels. Remove the 6th element and the 3rd element of the value of H and see that this is now a list of 3 elements, 3 atomics. If we do that, then in the 3rd element, the 6th element is removed. And you see that after 1/7 follows 1/9. Keep deleting. So this is the same line as above, right? Same thing. And again, I'm removing in the 3rd element, the 6th element, which was 1/9. So after 1/7, I get 1/10. All right, so we have 3 elements now in this association. I'm showing this to show you that length works on it, dimensions works on it. And as you may expect, first, last, rest, and most work, right? So this is just the first one of the association. The last one, that's the Hilbert matrix. The rest, that means that the first one only is removed, and most means that everything but the last. All right, this completes my second part about the associations. I will finish this with the third part in my next session. I'm coming to the second part about dataset, and the second session is about hierarchical levels. So I'm looking for a dataset with more levels, and that leads me to the Titanic example and then the moons example. So let's load the Titanic again. And I want my point in only 10 elements. I don't want to carry the whole Titanic with me, so I'm only using the first 10. And again, note the part notation, right? Part works on associations. So it's the pretty short 10 elements. So I think you may understand it better if I show you that dataset uses the concept of levels. And I'm using colors here to underscore that. Note these red parentheses, these red braces here. This is level 1, right? On level 1, we have the lines. Every line here, every association, because it's a list of associations, is on level 1. And then the class labels come on level 2. This is now like the column headers, and then comes level 3 with the values. So I think this may help you to understand how this proceeds. Now we always go red in the first position, blue in the second, and then if we have a third one, we go to orange. So let's look at all ages. And I have a hidden cell here because I couldn't evaluate it after it was in color. So these are all the ages of my 10 element subdata set. All right, so we go across all the lists. That's why all is in the first position, and first position means red. What do I want? The ages, right? Because every element has an age, and that's on level 2. We can have a third one, all ages, and then round to the nearest even. So red, blue, orange, all the ages, and then take it and round it to the next even number. So let's look at all ages that survived. If we look at this, then we get those 5 elements. And here the select is the first level, right? The select one is red because we're selecting from the outermost. The select works directly now on all these lists. And in this case, age again is our second level. I hope this makes it a little bit clear with these levels, right? The data set goes left to right if you think it about these levels. If you go from inside out, go right to left, the way I've shown it to you last time. All right, now let's use the planets data. My main point here is only the interactivity. A convenient top-level view with interactive drill downs. That's how I think about the data set. So let's load the planets. And the main interesting part here is, I think, the moons. And that is because every moon has a different number, every planet has a different number of moons. So if we look at it in the normal form, then it's a long list of data here. But you see that in level 1, we always have the planet, and that goes to an association consisting of a new association, which contains mass and radius, and then the moons themselves are an association. Why are they associations? Well, because they are different numbers of moons for every planet. So we see Mercury has none, Venus has none, Earth has 1, and Earth's moon is called moon, then we have it here. And then other planets have longer lists of moons. Jupiter here has a very long list, and Saturn and others. So if we ignore all this in detail, we can now do this analysis stepwise and go down interactively into these nested associations. So start with level 1, that was the planet, and it has a property mass. Okay, we query it, right? Level 1, level 2. Because mass is one of the sub-properties that we just saw for Earth. We can use bar charts. Now we have bar chart working on level 1. So bar chart works across all the planets. That's why it's in level 1. And everyone has a sub-property now, radius, and that's how we can do it so code efficient here. Show me all the moons of Neptune. So how do I have to go? Well, on level 1, I have to specify the particular item that I want on level 1, that was the planet. So it's Neptune that I pick in level 1. It has a property moons, and that's what comes in level 2 at this point. So there it is. There you have the moons. And the moons themselves have these sub-associations, these properties, mass and radius. All right, the planet masses, please. Now I want all the planets. So I have to use all in the first level and query on a level 2 for the mass. The radii, same thing, right? All planets, the radius. How many moons does every planet have? Okay, so we need to go across all the planets. The next level is the moons. And when I want to know how many moons does it have, I just ask for the length of the sublist or sub-association that I get. Obviously here it's associations and not list, but length works on both. Right? So here we see how many moons every planet has. We can further process the data set as if it were a traditional list. So how about a pie chart? Because a pie chart now can be applied to this, and we get automatic chart legends when we ask for that here. All right, which moons have masses heavier than Earth's moon's mass? So I'm introducing a new symbol here just to make the code a little bit easier to understand. But come with me through those nesting levels, where we're looking for Earth's, Moon's, Mars. So we're talking about one planet here, right? So we're not saying all, we are picking the one that we want on level 1. The next property in the nesting hierarchy is moons. So now we specify the moons. How many does Earth have? 1. What's its name? Moon. What property do we want? Mass. Right? So this is a very simple way to extract the mass of Earth's moon. And now we want to do a comparison against something from all of the planets. So now we say all, ask for the moons. On level 3, we are selecting where the mass, here this is the property on that level, is larger than mm, and we would like to have the keys as the left column. So here we have the moons that have a mass heavier than the Earth's moon. Which planets have radii larger than Mercury's radius? So I was trying to do something with a planet itself, and I didn't have a lot of options because the moons aren't all that heavy as I actually initially thought. So here I'm getting the radius of Mercury, right? So level 1, look up the particular one. Level 2, look up that property. So that's R now. And now I want to do something across all the planets, their moons. And here I'm now selecting where the radius is larger than R. Here it was the mass property. Here I'm looking the radius property and output with sorted keys. Here we are. So Ganymede has a larger radius than Mercury. Titan has a larger radius than Saturn. All right, for the next thing, I want to concentrate only on the moons, right? I want to extract the moons. I don't want to carry all that stuff that it's in sublists of planets, right? Give me all the moons. And to skip across the hierarchies, you can use Catenet. Catenet will just go directly to the moon properties. You can jump over it. And this is now a new data set that contains just the moons. And you see down here, 167 of them. All right, now I use the new dataset moons. You see that what follows is no longer on the planet's dataset, but on the moon's dataset. So I want mass versus radius, and due to the numbers, it's better to use a log plot. And there you see that, right? There you see mass versus radius of all the moons that we have. Quite a lot of moons, I think. This is equivalent as the following, because data sets and associations are supposed to feel like lists. And I think I'll talk next session a little bit more about when that's the case and when that's not the case, right? Data set, associations, and lists feel sometimes very, very similar, but they have very important differences. And I think I'll say more about that a little bit later. All right, so in the following, I'd like to show you a couple of queries on data sets and also point out a few things and a big trap that could happen to a programmer who is new to the data set and the associations. So here I have a portfolio, and that portfolio consists of stocks, and it consists of US Treasury bills. And this is just the raw data. I just assigned this portfolio to data. And I'm now looking at the headers. All right, we have symbol, description, quantity, price, and security type. I now turn it into a data set. What's better than using the association thread, because we have to thread the column headers over every element, delete the first one, because that's not our numeric data set, and then turn it into a data set, right? So DS is now our data set of this portfolio. And you see that this is a data set, right? You see it's clickable, and it's a gray shading, and you can click it and drill down into these things. All right, the association functions to create new data sets from an existing data set. It works without applying normal to the data set or converting anything back. I can now take an existing data set, apply operations with them, and I can create this new data set or this new display that I want by simply using these column labels. And we have them because this data set we've created was based on a list of associations. So we have a column symbol, And the new thing that I want to display now, I also want to keep symbols. So I'm using a column symbol. And what I'm using is, well, the column symbol that we had before. And given that we're going row-wise, we're using hash here. You see this is a pure function here. So this may still look boring because I'm just replicating what I'm doing, right? This is the new column label that I have, and I'm using the old one. So for the symbol column, that's what I want. Same with the quantity column and same with the price column. I want to keep them. But now comes total. And total is now the new column header that I want. But the way I'm computing it is that I take quantity times price. You may see a gray multiplication sign here, times the price. And another factor in this computation is that if the security type is fixed income, I want to divide by 100. Otherwise, my multiplier should be 1 if it's a stock. And you see that this is now a multiplication here. I'm multiplying 3 elements here. And I show these two side by side so that we can compare them better. You can do the same without the lookup, right? It doesn't have to be function application. You can go to the label directly. You don't need these brackets. So these are equivalent, right? If you say hash of bracket of the symbol string, or you remove them, you leave them out. So this will now give you these two associations. And again, they are associations. You can click them and interactively engage with them. All right, this brings me to an important caveat. You have to be careful how you construct the dataset. The dataset is smart enough to know how you constructed it, right? It's not just a table with numbers. In principle, every matrix can be turned into a dataset. So we could, for example, again, take a 5 by 5 Hilbert matrix. We prepend the column header, and now this is a dataset, right? It's clearly a dataset. If I ask for the head of it, I get dataset. Well, that's how I created it, right? And this operator notation, I now have dataset as the last operation on the right. So I have a dataset. But I don't think it's very useful. You see they're not clickable, the headers here. And they don't have a gray background. But it's not a list of associations. The header is no longer threaded across a list of associations. When you normalize it, you get a list of lists, not a list of associations. So when I look at the normal of this, then this is really just a list of 5 elements, just like the others. The fact that it's strings doesn't matter, right? It's now a 6 by 4 matrix. And all these ones don't know that they are columns under these headers, right? That's because I just created it as this simple table that I then forced into a data set. So you have to, the header row is now interpreted as part of the list, and it's no longer shared and clickable. You have to make sure that you provide a list of associations before you apply the data set. And if we do that, then, well, we get it, right? Now, again, they're clickable and gray. So I think this is a big trap that you may run into, because it's usually not all that useful to just take a matrix and turn it into a data set, because then there is no cohesion between columns, column labels, and rows and row labels. It makes for a very boring data set. So you should really make it an association, a list of associations, and then use the data set. Right? And if you had row labels here, you would use an association of association. I'm using a list of associations because I only want column labels. If I wanted to use row labels, I'd have to use an association of associations. All right, this brings me at the end of today's session. I've got about 10 minutes left. If there are any questions, I have 2 great assistants who will pre-screen some of these questions for me. If there are any, please send them now. We still have 10 minutes.
There is no question for now.
There's no question. All right. Well, then I guess I wish everybody a goodbye. And I hope I see you next time on our next session, when I will wrap up the associations and the data set. We look at query because it's so useful also for raw data. And then I hope I can get you ready for data scraping from the web.
Excellent.
Bye-bye.
Thanks, Andreas. Also, to our audience, please make sure to follow us on YouTube. Thank you. Have a good one.
Great, thanks.